So I'm just going to pull up we'll just look at a few. All right. And the reason you need the hydrolysis reaction is because you use those equations when you're doing like a weak acid with the strong base or vice versa when you get to the equivalence point. Because at the equivalence point, your moles of hydrogen are equal to your moles of hydroxide, which is equal to your moles of salt. So all of your hydroxide and hydrogen's been used up. So we can't go up with our regular way of calculating pH or POH to POH. So we have to use the salt instead. And that's kind of really the main place that you use them at. All right, so let's just look at just some real basic ones. All right, so if I had the salt sodium fluoride, all right, so I'm going to kind of talk about what we did yesterday. So you have to kind of think backwards and what acid and base they came from. So sodium hydroxide would be where my sodium came from, and that would be a strong base. And then hydrofluoric acid would be my source for my fluoride ion, and that is a weak acid. So the strong wins out, which tells me that I'm going to have OH as one of my products. So always start with your water on your reactant side. And now this tells me I'm going to have my OH minus. And then at that point, you're pretty well through with your strong because you do not use the cation or the anion from your strong. Okay. So now I need my salt. So my ion of my weak is my fluoride. So that becomes my salt. And then over here, I end up with my HF. This looks weird as a salt because it doesn't show the sodium, but that's because sodium is just a spectator ion. Remember, your strong will also contain your spectator ion. So what this is saying is that the fluoride ion is a stronger acid than the is a stronger base in the conjugate acid of the sodium hydroxide. So it's going to be the one that hydrolyzes the water. All right, anybody have any questions on that? So the way that the guy did it when I was looking for a video last night, because I couldn't sleep, he kind of, let's see if I can. So he does the same thing, and then he divides them up into the ions. So you have your sodium ion, and you have your fluoride ion. And then if you think of water as like we've been doing HOH, and if you think of this as your positive part, because that's your hydrogen ion, and the OH would be your hydroxide point part, then that's kind of how you work through these. So you got to say, okay, if I combine this with water, since my sodium is positive, it's going to combine with the negative part, because positive and negative, we want to get neutral. So it would give me sodium hydroxide. And then you have to say, is that going to really happen? No, because it's a strong base. So it doesn't want to say like this. It wants to say like that. So this doesn't happen. So that kicks that one out. And then you'll do the same thing with this one. I'm going to combine it with water. And since it's negative, it's going to combine with the hydrogen part, and I would get HF, and then the OH minus would be left over. And then you think, well, is that going to happen? Well, that stay. And it will, because HS is a weak acid. Okay. So anyway, I hope that clears it up maybe a little bit with that. The ones that I've kind of getting kind of some mixed answers on are some of the ammonium ones, and I've kind of seen them work two different ways, and so I'll kind of clarify that as I get it figured out next week. So we will have a quiz tomorrow, not tomorrow. We will have a quiz on Friday, And it will, I'm going to show y'all in a minute a couple of full titration problems, and they take a lot of steps, you're going to see. There will not be one of those on that. So it'll be the things that we covered. So there may be some KB problems, which actually go back to the notes. There may be some basic writing of hydrolysis reactions, and but it won't go all the way up to these titrations that I'm getting ready to show you right now. And the only difference in that would be if it was a strong titration, because if it's strong, you don't have to go through all these steps and figure out the salt. Okay, so those are like we did in Chem 1, where you can use your let's see, my N of my acid, my V of my acid, my M of my acid, and set that equal to your base. You can use that only if it's strong. And remember your acid, that's acidic hydrogen, usually at the front, not all the hydrogen, and for your base would be how many hydroxide groups you have. All right, does anybody have any questions on that? All right. Oh, get my thinking bits on here. So I was going to go back a little. So hopefully you watched the titration curve video. If you didn't, I suggest you do. You have the notes that go along with that. And let me see what I want. Make this Rollins a little bit lower, a little bit littler. I have been, I probably closed it out. Probably would help if I closed my mic. I know. I can't remember what meeting I was at. Somebody was like, do you think you have enough tabs open? I also do the same thing. If you look at my desktop, it used to drive Miss Parker nuts. How many things I had. All right, where was I at? Those points of titration. I guess it was farther. When I try to help Miss Corman, she always does, like, she closes out each one before she opens a new one, and that drives me nuts. All right, I feel like I'm not in the right notes, but am I not in the right notes? No. We are. There's hydrolysis. They're just longer than I remember. Acid. Nope. That's at the end. So it must be one of these. Yeah, it was. Before. All right. There we go. I think I just passed over those just a minute ago. All right, so let's see if we can do these. All right, so the 5 points of interest that you might see on a titration curve. So what do we got up here? We got number 1 going. Oh, maybe my thing won't load up and then I'll. Answer. I am. It's been that kind of week, and I can't believe it's only Wednesday. It's like it's much longer. All right, Lord have mercy. Okay, let me get Miss Baker out of the way. All right, so our 5 points. So the pH before the titration begins. So remember, when we're titrating, I cannot draw, but remember, you have usually a beaker down here and then you have a burette. And so you're going to know the concentration of one of those. So before it ever begins, let's say that our unknown is in the burette. So that means I have my known down here, and I have a given amount of that in there. I haven't, so let's say it's acid, all I have is acid. I haven't added any base or vice versa. So at that point, I know I can do this. All right, so at that point, then you only need to figure out what your pH is based off whether it's a base or whether it's an acid. If it's a strong one, it's easy. If it is a weak one, then you're going to have to do your rice table like we've done already. I wanted to do. All right. The pH on the way to the equivalence point. So that one is whenever you're in a buffer system. So it takes a little bit more work. So as soon as you put your first drop in from the burette, then that's going to change not only the concentration of what you're dropping in from the burette, but also what is in the beaker. Because let's say you have an acid that's in the beaker. Once you drop some base in it, then it's going to have to sacrifice part of its hydrogen ions to form water. So that's kind of what we've already done on some of the problems. So we would use this formula that we've been using. Whatever is the added part in the burette has to be subtract from the other component. So let's say that I was dropping, let's say I was dropping acid. I don't feel like that's, let's say that I was letting acid come in from the burette. So that means that I would need to add to here, and I would have to subtract here if it was an acid. If it was a base, it would be the other one. If I was started with just a base in there and I added an acid, then I'm going to be doing the opposite of that. And we've already done some problems where we did that a little bit. Do y'all remember? I'm glad y'all do because I kind of know. But all right, so the pH at the midpoint, this explains a whole lot of it, but this is probably the most important part out of all of that. And that is, you're going to see in a minute when we do these long problems, that's like the easy part. That's not where you're at the equivalence point, which is when you're halfway there. So usually you're given the Ka, so you can just take the negative log of it, and then that tells you what your pH is, which is usually the question that is being asked. So that's my favorite part. Then you get to the equivalence part, to me, the hardest part. You're going to have to calculate the pH of the salt. So this is when you have to write your hydrolysis reaction. And sometimes you may only be given Ka, and when you write your hydrolysis reaction, it's actually like the reverse of the acidic reaction. So you have to use the 1 × 10⁻⁴ to figure out your Kb. So that's why this involves a lot of work. And also remember, the reason that we can't use our hydroxide concentration or our hydrogen ion concentration is because all of that's reacted and all of it's turned into a salt. At this point, your moles, not your molarity, your moles of your hydrogen ion are equal to your moles of your hydroxide ion, but those are used up. So then I have to depend on my salt. Since this is also going to be equal moles. All right. And then once we get past the equivalence point, then you're going to end up with just one thing in excess. So if you were what's coming out of the burette is an acid, once you go past the equivalence point, then you're going to have excess acid. So you would calculate the pH just using that. If the base was coming out of the burette, then your excess would be the base, and you can calculate, bless you, calculate your pOH, and then subtract that to get your pH. And that part's not usually too bad either. All right, so let's look at this extremely long problem. Can y'all tell I'm kind of procrastinating a little bit with it? All right, I think it's a little bit farther. We already did all this, yeah. All right, here, is this where we're at? Yes, no? Oh, just the A part, oh, good. All right, so we already did A. That makes me happy. So now we're going to do B. So at B, let me split my notes here. Catch up with it. At B, we're at the halfway point. So that is when our pH is equal. I think I'm just going to leave it off of that since I can't seem to do it correctly. All right. Let's just try this now. All right, y'all tell me if y'all can't see and I'll figure out something. So here, this is when my pKa is equal to my pH. So that's going to be your easy one. So they gave us our pKa somewhere, which was 6.2 times 10. Ka was 6.2 times 10 to the negative 10th. So I can just take the negative log of that. 6.2 times 10 to the negative 10th. And then that gives me 9.208, which is equal to my pH. So that by far is the easiest one. Once again, this would be easy point or point on the test, but if you just go from here and all of a sudden write that number down, you're not going to get any credit. You got to show them where you've gotten that number from. You usually have to prove what you're doing. All right, so let's move on to the hard one. Are we at the hard one yet? I don't know if we're at the hard one. It's more room. I'm going to have to probably just pull up. I can't get it fit on here. So I'm just going to pull up a piece of paper and work off of that because I write too big. All right. So now we are at the equivalence point. So we're on C. So that's whenever we're going to have our moles of hydrogen equal to our moles of hydroxide. And then that's going to be equal to our salt. So if this is when we need our hydrolysis reaction. So what we're reacting here is cyanic acid and sodium hydroxide, because our salt that we end up having is sodium cyanide. Okay, so that's where those two originated from. This is my strong base. This is my weak acid. So that tells me I'm going to have hydroxide produced. So I'm going to do my little H. And then I'm going to have negative OH. And then I'm pretty much through with that. The anion of my acid becomes my salt. And then over here, I end up with HCN. So this is your salt. Once again, it looks funny because you don't have the sodium attached to it. So you could, on my next step, I do here, some people choose to do it a little bit farther down. But what I noticed from this is not an acid problem. This is a base problem, because here my CN is accepting a hydrogen. It's not giving up. So you can see it's like the reverse. So I need a KB and all I have is a Ka. So I like to go ahead and do that step. So my KB is going to equal to 1 times 10 to the negative 14, which was my Kw for water. And I'm going to divide that by my given Ka. And where I got that from is when we've used the relationship of KW is equal to KA times KB. That's where I got that from. So when I do all of that, I end up somewhere in my very messy work, 1.61 times 10 to the negative fifth. All right, did we get on that so far? So I'm going to run out of, so I'm just going to jot that down here so I won't lose it. 10 to the negative fifth. All right, let me get some of this erased. Oops, I'm not gonna do it. All right, so I need to know now how many erase the wrong one. All right, so I need to know how many millimoles of my cyanide ion I have. If you look back, and you'll have to flip it over, it tells you at the very beginning that for your acid, you added 50 mils of 0.1 molar. That's all the acid that was ever added. I'm going to leave that in milliliters and do millimoles times 0.1. And that gives me that I have how many millimoles of my acid? 5. Okay. So if I have 5 millimoles of my acid, then I have to have 5 millimoles of my base. So here I know this part. I know that it's 0.1, so I have to think, and it's nice here because it happens to be the same number. How many milliliters would I have had to add to get there? 50. And the reason you need that is because you're going to need this total volume, because our next step, or eventually our step will be to get the molarity of our cyanide ion. So that means if I have 5 millimoles of all of those, then for my cyanide ion concentration, it's going to be 5 millimoles, because that's the definition of it. That's why we use the salt, divided by my total volume, which was 100 mils, and that gives me 0.0500 molar. And that's what I now can put into a rice table. So does anybody have any questions where I got any of those numbers? Not too bad. All right. So let me regroup. All right. So now we're going to do our little rice table. So here my initial is my 0.05 that I just went to all the trouble to figure out. We're not worried about our water, and we had none and none. And really at this point, some of y'all may not need to write a rice table, because what's it going to end up being? X squared divided by 0.05 minus X, right? So anyway, I'm gonna go ahead and write it out. But you know, we've done so many of them. And as I told you, I'm not going to give you a quadratic on any test that I give you, because I don't know how to solve it in my calculator. So, and it's not, I mean, chances are you're probably not going to see it on the AP test either. So I'm going to lose X of that, and I'm going to gain that over here, because everything's a 1-to-1 ratio. So at equilibrium, I have 0.05 minus X, and this is X, and this is X. All right. Remember that we're trying to, after all this, I kind of get lost. We're trying to find our pH. So I have my KB, and if I look at my KB is equal to my hydroxide concentration times my HCN concentration divided by my salt concentration. Okay. So we know our value for KB, that's 1.61 times 10 to the negative fifth. Both of these here were X, so that's why I'm going to end up with X squared. and my cyanide ion was 0.05 minus X. And we are going to neglect X. We're going to assume that it's so small it doesn't matter. So I'm going to put what I got in there, and then hopefully y'all will get the same thing. Lena, wake up. All right, so does that work out with the calculation? All righty. So can I just take that and get straight to my pH? What is this X? This X actually represents what concentration? Yeah, it's going to represent my OH concentration. So I'm going to have to go through POH to get there. So sometimes somebody may do all this hard work and then at the end think they've already found the pH. So I'm going to take negative log of my 8.97 times 10 to the negative fourth. And that is going to give me 3.047, which is my POH. So now I need to get my pH. So I'm going to take not 15, how about 14 minus. And finally, I will get my answer, which is 10.953. And I'm going to say that is equal to my pH. And I'm going to put it in the box because if I did all that work, I want every point that I can have. Sig figs, 3 sig figs, because our different, if you look at your measurements at the front and your concentration, everything was in 3 sig figs. All right, does anybody have any questions on that one? Because I need, this is what I needed. I needed that concentration right there so I could relate it to eventually the pH. And so that's what, so that was where one of my X's came from in the KB. Does that answer your question? Anybody else have any questions on that? All right, let's look at our next one. I don't know, it looks like I think we'll finish, we'll work it out. All right, let's see what we got going on in our next one. All right, so in our last one, what does it say? Oh, no, that's it. We're through. Never mind. I was doing another long one today where we go past it. That's it. It's a lot of work. All right, anybody have any questions on that? Don't worry, because I'll give you a chance to practice here momentarily. All right, let me try to go back to get to the slide. All right. So talk real quick about acid-base indicators. So the endpoint and the equivalence point by definition are not really the same thing. The endpoint is when the indicator changes color. So like we did phenolphthalein probably a couple of times, so it goes from clear to pink. And if you've chosen your correct indicator, then the equivalence point and the endpoint should be as close as possible. All right, I think I've kind of just summarized that whole little bit already. So there are kind of some tricks on that. So indicators are usually weak acids. So that's, if you ever see, it seems like we've already had an FRQ where you saw this. That means it's an acidic indicator is what the IN stands for. And usually they're one color there, and then whenever they lose their hydrogen ion and they form their anion, then they're usually a different color. So like here's phenolphthalein, I kind of already mentioned that. And usually you have to have at least 1/10 of the initial form of the indicator before it's going to change colors. But after all that, this is your useful range. If you have the Ka, you want to find the pKa, and then you want to compare that to a chart and choose one that's about plus or minus 1. so that that will be the correct indicator that will change color at the correct time. So choose a Ka that's of the acid that you're titrating and whose color changes strongly at the equivalence point. Okay. And we'll, in a minute, we'll look at a chart and it'll make a little bit more sense. The chart in your notes. So here, I don't know why I keep on doing that. Closing it out. All right. So let's say that this is our chart. Okay. So it says we want to decide which indicator would be best to use for the titration of ammonia with hydrochloric acid. So this ammonia is a weak base. Hydrochloric acid is a strong acid. So when I get to my equivalence point, what is going to be my pH? Just a general ballpark. 7, above 7, below 7, below 7. So I'm going to have a pH that is going to be less than 7. Is that the way that you write less than 7? All right. So then if we look here, we can look at our transition ranges, and we want to kind of match it up to the one that transitions or changes color at the closest pH. So which one do you think would do that? I mean, you could get all rid of these on each end, right? So this one, it seems like this one and this one are in the running. But if you look at this one and you compare it to this one, notice this one goes actually a little bit over 7. So if I have a strong acid and I'm making it with weak base, does that make sense? Or does this one that changes at a more acidic pH make sense? Yeah, so that's the one you're going to choose. So you would choose methyl red on that particular one. And if you get one of these problems, it's going to be like that. Usually there's going to be some you can get rid of real easily. And then think of what you're titrating and think of when the color changes. And then you're going to probably have to choose one on either end. You'll probably get a couple that seem like that they could work pretty well. But this one, since it goes all the way up to 7.6, which is a little basic, that's not going to happen until I go past the equivalence point when I have some excess ammonia. All right, I don't need to do that. I need to do that. All right, so I think the next one is a little bit different. It says bromothymol blue has a Ka value of 1 × 10⁻⁷. And it gives us a whole big story. If the solution, let's see, what do we have? We have a strongly acidic solution, and it's being titrated with sodium hydroxide, which is also a strong base. So what do we know that's going to happen? What's going to be the pH at our equivalent point? Strong acid and strong base. It's going to be 7. So at my equivalence point, your pH is going to be about 7. So we want to match it up, and remember that this is my Ka value. If I have a Ka value of this, what's my pKa going to be? Do I even need to put that in my calculator? No, it's going to be 7. Okay. So both of these things are telling you that it's going to change. It's going to have an equivalence point at about 7. So you would want to choose something that changed colors, because this asks for a range or a number between pH of 6 to 8 to kind of cover each end. If for some reason our Ka value would have been 1 × 10⁻�3, that would tell me a 3 is my pKa value. So I need something that changes color when it's a lot more acidic. All right, anybody have any questions on that? All right, so I am giving y'all, y'all got them already, I forgot. All right, so these are 2 long titration problems, one on the front and one on the back. Row, sit up. And y'all need to do these and turn them in at the end of class tomorrow, okay? So give them a try. Try to just go off your notes. Don't Google. That's not the point of this, okay? Yes, sir. Okay. Can you email it to me, you think? Snap a picture and send it to me through Sports Shoe, maybe? Okay. If you can, then if not, bring it on Monday, okay? Who's missing? Michael, can I give you this one, Glenn, in case Glenn and the stuff are back for? Okay. All right, so y'all turn those in to Mr. Anderson at the end of class. Once again, we'll go and Google it because I gave it to you. That's not gonna help you, okay? All right, and then a quiz on Friday, but it will not be one of these real long problems like that. I feel like that one problem would take the whole entire period if I did that. All right, let me turn off